Hello and welcome to lecture 25. In this lecture, we'll talk about something that's known as the kernel trick or the kernel trick mechanism. And why is this such an important topic in machine learning in general, especially in support vector machines, is because this allows us to use non-linear feature transform without actually getting into the feature transform space. And that is I would say, the big focus of today's lecture. And before we do that, let's, as always, recap what we did last time. So, last time we focused on the evidence, like both experimental and theoretical, that kind of uh, pointed us to the fact that maximum margin is better, right? A fatter margin is better. And then we also looked at an example where we reformulated, or in fact, built on our optimization problem for the maximum margin, and we had this hard margin earlier, but then we figured that there can be non-separable data scenario, and in that case something that's known as soft margin comes up, and that's the or like this problem here. And the thing with soft margin is that we are allowing some form of penetration that's given by this like epsilon or z, whatever you like to call that variable, and that's the amount of penetration that we are allowing. In a sense, we are introducing a trade-off between the in-sample error and the regularization that's controlled by C, right? And then we also looked at like another way of like to use feature transform. I wouldn't say like really another way, but we were using feature transform and then applying the maximum marginal separator instead of like what we used to do earlier when we had like a linear model. We would apply like an appropriate model then. So what we like the thing to really notice here is that when we moved from this third order polynomial to the second order, of course, you see that there is a huge difference in the number of dimensions, right? And the regularization constant of this maximum margin was making our model more robust in some sense. So what happened in second order, we get a comparable result because it's like, again, it's what's really going on behind the scenes is that really the support vectors that are controlling the final hypotheses, right? So it's making it robust, and simply going from like 5 to 6 support vectors, like, or maybe like the other way, like going down by one support vector, you're like really not in that higher dimensional space, right? So therefore, like what we are saying here is that like with an addition of one support vector, we are going in that huge, like larger dimensional space, and that also pointed us to the fact that can we like keep going? Can we go into a really like higher dimensional space at all? And well, in certain sense, we will try to answer that, of course, today. And the other thing that I wanted to review before we move further is because we will talk about this nonlinear transformation, this transformation into the Z space. And so I quickly wanted to review what we said because this lecture was some time back, if you remember. So what exactly was the case? The original data was not linearly separable. And so I applied some function, which is nothing but a feature transform. And then my entire data was like viewed in the Z space because now my data is linearly separable and I can implement the linear model, right? And in our case, maybe that model can be the support vectors, the maximum margin, right? And then what happened was once we were in this space, we applied the model, as you can see here, so separate data in Z space, but then we had to report it. So that means I have to go back to my X space and report the classification based on this classification result that I got in the linear space, right? So this entire process, like if I call it a process starting from step 1, 2, 3, 4, the fundamental idea here is that I'm taking my data and moving it into another space altogether, right? And this, in a sense, is a physical constraint, right? That's preventing us from going into huge dimensional space, which is like an infinite space. So of course, like I get like some feasible space, that's my Z space, but then imagine the number of parameters in this like sort of transformation. Imagine the dimensions that I can add to my data, and sometimes that can become a problem because it becomes computationally challenging. So what we are really trying to focus on today is that can we do something about like these dimensions essentially, right? Can we do something about that? Because like although we have like these like d bar dimensions, in Z space, but also we have to think about like we're not really reducing them a lot in any sense, right? And so we have like these huge number of dimensions and have to work in that. Of course, we made due to some definition of my phi, I made it like linearly separable. That's fine. But can we do better than that? Let me put it that way, right? So let's like really come to today's lecture and the real problem that we are trying to answer or real question that we are trying to answer is how to use non-linear transforms without physically transforming data to Z space, because we understand that we were able to make our data ready for the linear model, but the computational challenge stayed with us, right? So like as I said, we have seen that with the when we were working with the optimal hyperplane, right? We saw that we have the ability to use that optimal hyperplane to control the overfitting. And that was happening almost independently of dimensions. That was the focus, in fact, the focus of the last lecture, the towards the end. Okay. So now if we have the ability to go to higher dimensions without physically, right, physically transforming or going into the Z space, then I can save myself from the computation that involves like physically transforming my data into Z space, right? So that's like one battle won. Then, of course, a lot of things will change in my optimization problem, because my optimization problem in my optimal hyperplane or my fattest hyperplane or the maximum margin hyperplane, whatever we like to call it, right, has a dependence on dimensions, right? And so we'll have to do something there, and let's see what we can do there so that we can actually move into like transform the data into Z space, but not like physically do everything. All right. So I'm beginning by re-looking at the quadratic program that we formulated some time ago for the optimal hyperplane, right? The maximum margin hyperplane. And this was the original problem. So if you remember, my original problem looked something like this: minimize for the W's and the B's, because we are solving for the weights and the bias. W transpose W, and then subject to the constraint yn W transpose xn plus b, that's strictly greater than 1. And this was for all n, that is from 1, 2, and so on up to n. Okay, so what is going on here? So this is an optimization problem. This is a quadratic program. Again, repeating it. And so why do we solve an optimization problem? Well, we solve it for optimization variables, right? So how many optimization variables are there? If like this is a d-dimensional feature space, then I have like d plus 1 optimization, and let me like say this, optimization variables, right, in this problem. And what about this? Like how many number of constraints? Well, the number of constraints are dependent on this n. And so like if n is like n, this big N, right? So I have like N constraints. Right. Now we can use the nonlinear feature transform, right, and run this quadratic program in that Z space, in that like whatever space that is, right? But then the problem is like with D plus 1 optimization variables, the number of features in my transformed space will be huge, right? As I said just time, like in my like transformed space, right, in my transformed space, I will have like large number of features. Okay, so what's going on? Like, of course, this is not good because computational challenge is there, and we want to address this. Like, we want to be more efficient when solving this problem. So maybe we can do something with the optimization problem itself and the way we solve it, right? And what we're going to do is this, in like the way this problem is stated is known as the primal. And of course, if you've taken any optimization class, you'll know that this like the basic formulation of any optimization problem is the primal form. And what we can do is every primal has an equivalent problem that exists, and that's known as a dual. All right. And so this is like a joke in the PhD community that like you are a PhD student only if you can convert the primal to the dual and then solve it. So yeah, I mean, jokes apart, there exists an equivalent, I would say, formulation of this optimization problem, right? And why is this important and why we use it so much is because what happens in certain situations is that like I have an optimization problem that has a lot of variables, right? And fewer constraints. And the constraints like are in some way determining my feasible set, right? And to solve an optimization problem with so many variables sometimes becomes difficult, and so it's easier to like get an equivalent problem that has lower number of variables and maybe more constraints. So that's exactly what we achieve with the dual, and that's exactly what we're going to do here. So basically for each constraint, what I'll introduce here, for each constraint in the primal problem, I'll introduce something that's known as the Lagrange's multiplier. And of course, you must have come across this. So the Lagrange's multiplier will help us create the dual form of this, right? So what is exactly Lagrange's multiplier? For each constraint, I'll have one Lagrange's multiplier. So essentially, I'll have like a vector of some alphas, where for every constraint, I'll have like alpha 1, alpha 2, and up to like n, right? And again, as I said, it makes our problem easier because, of course, I have like this bigger objective function. Sometimes the constraints become really simple. And sometimes like I achieve some like reduction in dimensionality, so that helps, right? So let's look at like what this dual formulation will look like. And so what I'm doing is I'm saying minimize over alpha. So these are the Lagrange's multipliers. As I said, there will be like alpha 1, alpha 2, and alpha n, right? Minimize half of, and then all these will be summed up. So it's more like a weighted sort of sum or something. Think of this as that, this expression. And of course, there is no need to like memorize it in any way. This is just like showing you that this is another way of formulating the same problem. And this is going to help us in like understanding a few things, that's all. So here, n and m are essentially coming from the same data. So they are like practically the same thing, right? yn, ym, xn transpose xm. Okay, coming from the same data set, almost the same, right? So both n and m are data points. And what we are doing here is we are taking the inner product of that and minus the sum of, and this is like a standard procedure to write it in this way, minus the sum of all these alpha i's, right? And there are certain constraints, obviously, that will come up. And let me write them. Alpha n, yn 0. And one of the most important constraints is that these alpha n's have to be at least 0 or greater. So they cannot be like, they have to be non-negative, right? And the thing with the dual, and this is like the dual formulation, is that we are solving for a different optimization variable. Here we were solving it for w's and b's, right? Here I'm solving it for the Lagrange's multiplier, that's alphas. And so when I solve this, right, the output of this problem has to be some alpha n, or maybe sometimes you like to call it alpha n star for the optimal, right? And again, this is also a quadratic program. It's pretty easy to see that, pretty easy to formulate that, because this here can be like written as alpha transpose some matrix times alpha. So that's like these alphas will become the u's, and so you can like convert that. So I'm not going into that, but this is also a quadratic program. And so we know the way to solve it, and we can get this alpha n star. Okay, so what does this mean if we get like my alpha n star? How is it useful? Because like my original problem was to get the w's because I need the optimal hyperplane, right? And so of course the way to proceed with that is that there exists a relationship, and that can be derived. And so that relationship in this problem is something like this. So we can get the optimal weight, which is like n goes from 1 up to n alpha n star yn xn. This is how we can compute or extract or calculate, whatever you like to call it, w star. And also this like the bias, the optimal, right? So to get this optimal b star, what we do is like we pick a data point s, like whose alpha s is greater than 0. Like in order to calculate this, like I'm writing it here, pick some point s whose Lagrange's multiplier s is strictly greater than 0, and that is nothing but a support vector. That is going to be a support vector, and utilizing that we can calculate y. So then it shouldn't be y star. We don't have that. I'm sorry. I meant just ys, not star. Yes, so I meant ys for that point s minus whatever optimal weights we calculated, transpose xs. right? So that X is my support vector, right? Now, again, like as I said before, why do we care about this dual so much? Well, we care about the dual so much, and as I said when I was beginning to talk about what primal and dual relationship is that if we look at the dual, right, what we have is like these optimization variables. So that's what we need, right? These alphas. And they are n in number, right? And so let me write it down. So in my dual, what I have is like n optimization variables and optimization variables and n, like what exactly is n, right? N was like the original like number of data points, right? The other thing is also looking at the constraints. Now, if you go back to the constraints here, they are way simpler than the one that was there in my primal, right? In terms of like, if you generally think about it, it's mostly like pointing to this fact that like these are like non-negativity constraints, I would say. And how many of these would be there? Well, of course, like n plus one, because we have like these many here. So maybe n plus one constraints and just like non-negativity constraints, which is like simple, right? So I have this formulation. And also, like if we think about the original problem, right? The number of variables was n. Sorry, the number of variables here is n, while in the primal, the number of variables that we were solving for was d, right? So d was the data dimension. And although we have formulated an equivalent problem, which is a dual, right? But then the important thing here, like why we did it is because it does not depend on dimensions. So it does not depend on dimensions. And that's like, I would say, loosely speaking, not like strictly speaking, that is the goal when we formulate a dual and then solve it mostly. Because as I said, you have like more dimensions and you don't want to, optimization becomes difficult as we move into higher dimensions. And so that's why we formulate a dual. And it's an equivalent problem. It has been proven. So that's an equivalent problem, just like flipping the constraints to the objective function and doing some changes there, right? So what we have done in this particular case, in our problem for the optimal hyperplane, what we have done is we have traded the dimensions, that was like my D, right, with the number of data points in some ways, right? And because you're solving for the like number of variables, that is n. Now, of course, we can see that like we got rid of my D, so there is no explicit dependence on D, but there is this implicit dependence on dimensions in this, the objective function for the dual as well, especially here when we compute the inner products here. So then there is like that those points sit in some dimensional space, right? So in a D-dimensional space. However, like we do not have to like deal with the dimensions explicitly in the problem. But if we can compute this dot product, like this xn transpose xm, without going into high dimensions, and that's like great, right? But then we also need to compute the weights here. So this also has like some implicit dependence on dimensions. And first of all, why are we computing the weights? Well, we are computing the weights. Why do we compute the weights? Well, we get the final classification using these weights, isn't it? That was the whole point of having these weights. So if we can somehow get this classification, this final answer, right, without computing these weights explicitly, then we have succeeded in completely removing the dimensions, right? And so that's what this primal dual relationship does. And let's prove how this does that, right? How this primal dual relationship gets us completely free of this dependence, this explicit dependence on dimension. So let's try looking at that. And of course, like I'm going to do some formulation here in terms of, and these things are quite common when we do convex optimization. You must have come across it if you have taken optimization classes. And what I'm doing is I'm introducing a term or a function that's known as the Lagrangian. And I'm very sure you must have come across it somewhere. And what this does, like in general terms, again, the same idea, the idea being that we are trying to formulate an optimization problem that is simpler in terms of like how we can solve it, right? And so what happens is we create this Lagrangian function that is dependent on my optimization variable that are w's and b's and the Lagrangian multipliers. And the objective function is essentially the sum of the original objective function plus the Lagrangian multipliers times the constraint. That's a function. And I'll show you how we formulate it and how we will like approach solving it. Of course, we won't exactly prove what we are trying to prove, which is the optimality condition, but we'll talk about the intuition. Okay. So this is L Lagrangian, and then this is Lagrangian. If the spelling is wrong, please check the textbook. Maybe I might have spelled it wrong, but that's alphas are still the Lagrangian multipliers, and my function will now become half of W transpose W plus the sum over all n's and alpha n1 minus yn W transpose xn plus b. Yeah. Okay. So the way we formulate this Lagrangian is that we bring all the constraints in here in the objective function itself, and we put it in a form. Here we have put it in a form, something that is less than equal to 0, and that's multiplied by this alpha n. So that's what we somewhat have here, right? And so we can derive that condition like taking 1 minus yn times some positive value here. And so that's what we have formulated here, right? So this is a standard procedure in optimization. And what do we require? Well, we require one more thing, which is alpha. All the alphas have to be greater than 0, right? So now, okay, so each is fine. What is the intuition behind this function, right? So let's think about it. So the intuition is I should be able to minimize my L because it's like putting everything together such that it has these Lagrange's multiplier and has like these weights as well. So what I have to do is I should be able to minimize this L, right? And of course, with respect to my, and let me write it down, with respect to my W's and B's. This is what I'm trying to do. And like another advantage that I forgot to mention here is that this is like an unconstrained optimization problem, which is always easier to solve than a constrained one. So that's another reason why we put like any difficult to solve optimization problem in this Lagrangian form, right? So what exactly am I trying to do? I'm trying to minimize my L with respect to my weights, right? Or like another way to think about it is that I'm trying to maximize my L with respect to my alphas, right? Because my alpha n, essentially what I'm trying to do is alpha n greater than 0, because then only we'll get the solution to my original problem. Then only I'll get the optimal solution to my original problem. So this is exactly what I'm doing in this problem. So either do this or this, both should work well with the overall result. Okay, so the proof to kind of show what exactly we need to do here is like a form of an intuition, I would say. We're not like exactly doing proof. This will just like show you that this is like an intuition to solving this problem. All right, so looking at this part here, right, we can think of a lot of things when we look at it. Well, one thing is that either, like there are two possibilities, first of all, right? So there are two possibilities for this particular term. So either my 1 minus yn w transpose xn plus b is less than or equal to 0, or the other possibility is that my exactly this thing, w transpose xn plus b is greater than 0 for each n. Right, so like either one of them is possible when I'm trying to solve the problem, right? So what do I have to look at here? Like consider this case, consider this one, the second one first. So if we have this situation, right, and we go back and look at my original Lagrangian, right, which I'm trying to either like minimize for my weights or maximize for my alphas. When I look at that, only this term here, what's going on here? Well, if I want this to be true, like if I want this thing to be true, which means like I want this to be positive, right? And obviously, if it is positive, then if I multiply alpha n by this, yn w transpose xn plus b, right? For this to be like greater than 0, right? I have to make some choice for my alpha, right? And make a choice for alpha that is like the best choice. So the best choice here for it to make it like greater than 0 is that alpha has to be like really, really large, right? Maybe so much so that it's like infinite, right? And so, yes, L here, my L will take a large value, which is okay because I'm also trying to maximize my L with respect to my alphas. But we also have to not forget this term, and that's exactly the purpose of like having this Lagrange's multiplier, because if we have like these two balancing objectives, then we can really like put both of them together and then solve the problem. And so this is like kind of showing us this is the way to go about it, right? What I've done is I've put both the objectives together. And so if I'm making this alpha n really big and making my L go to infinity, this is not what I can go ahead with, because my L will take a huge value, a large value. And my another objective was to minimize L with respect to my weights and my B, right? So I have like these competing goals because I need to pick my W's to minimize L. And so I have to achieve that as well. Okay, so to achieve that, maybe what I can do is maybe I can look at this other possibility, the first one. Let's call it like the first possibility. The second possibility we already looked at. So let's look at this possibility. 1 minus yn w transpose xn plus b less than equal to, it was less than equal to, right? Yes, we just took the strictly greater than case earlier. All right, so we have to do something with this one. This should be the case then, because the first one is like not possible, right? And so if this is less than 0, right, we have to think in terms of my W's and B's, because like we are trying to minimize the L. And at the optimal solution, if this term here is greater than 0 that we saw earlier, that is not possible because like my alphas have to be really huge and L becomes huge. So that's not optimal for my second part. Now at the optimal, maybe we can think about this one to be the case, because like that one is not the case. So obviously this has to be the case, right? And if this has to be the case, then this implies that essentially, and because if I rearrange terms, this implies that my yn w transpose xn plus b is greater than equal to 1. This was my like original condition, right? And so this implies that when we do achieve the optimal, the data is separated, because this is like the separability constraint. And so like we are getting some pieces of the original problem here reappearing, right? And again, like within this part, we have like two scenarios. One scenario could be that my 1 minus yn w transpose xn plus b equals 0, right? Or my 1 minus yn w transpose xn plus b is less than 0, right? We can have like both of them, either one of them. So now we are optimizing with respect to my alpha n's and trying to maximize L, right? And the quantity like this, if I multiply this by my alphas, right? And so this quantity, this alpha n times this, less than equal to 0 if I'm considering this like this original one, right? If I'm considering that, and also I know that my alpha n has to be greater than equal to 0, right? And the only possibility, the only way out here is that this thing has to be negative, right? This has to be negative for this condition to hold, right? And because like we are trying to maximize, so the best we can do here is to get this equal to 0 or alpha n equals 0. Either way is okay, right? So in either case, like alpha n is 0 or like this thing is 0. So the two conditions that we finally arrive at after looking at all possible scenarios is either this or this. So either this thing is equal to 0 or my alpha n has to be 0 at the optimal, right? And if that happens, then what happens in my original Lagrange's equation is that the second term will go to 0 at optimal, right? All right, so that was a lot of information. Let me just like summarize what we just said. So what we just said is that at the optimal, my alpha n times 1 minus yn W transpose xn plus b has to be 0, because we just like figured that the other case when it was strictly less than 0 was not possible, because like either because alpha n is positive, so this has to be negative, which wasn't a possibility. So here we are looking at this exact equals 0, or like another either alpha n is 0 or my this thing is 0. One of them has to be 0. And if this is exactly equal to 0, then this is pointing to the fact that we have W transpose xn plus b equals 1, right? And this here, this point xn here, because this is true, this here is exactly the vector at the margin, because like my 1 is considered to be the margin. So what does that point us to? It points us to the fact that xn is a support vector, right? Or it's on the margin, right? In either case, like either this has to be equal to 1 or alpha n has to be 0. All right, so these are also known as the KKT or the Karush-Tucker necessary conditions for optimality. So if you ever come across the KKT conditions, this is what it is. It is a necessary condition for optimality, and the KKT condition at optimal is 0, which is telling me that my Lagrange's optimal is half W transpose W, because the second term is gone. So either this has to be 0 or this has to be 0 at optimality, right? And of course, what we are saying here is that like this thing yn W transpose xn plus b greater than equal to 1 is my constraint now, right? So what does this like mean? This means that we have I mean, if we are looking at this, like this KKT is like a condition which tells us that any constraint that does not satisfy this condition will have a 0 Lagrangian multiplier, right? So that's why we have like an alpha n equals 0. And so this is the condition for optimality. And what we are saying is we have, like this will have been minimized, this thing, this L has been minimized with respect to my W's and B's. And we just prove that the constraints are satisfied at that, right? So basically this was a high level proof, not a rigorous one, that shows that L is closely related to our primal, the original problem formulation. And all we have to do is like minimize L with respect to my W's and B's. And we know like when optimality happens, right? So either we have to minimize L with respect to my W's and B's or maximize L with respect to my alphas. All right. So now after having proven the optimality, like the necessary condition for optimality, we have to actually solve the optimization problem. So in the next video, we are going to look at that.